Greetings everyone, welcome back to video lecture series on VLSI design. My name is Dr. Prashanth Bachanna, working as Assistant Professor in the Department of Electronics and Communication Engineering at Institute of Aeronautical Engineering, Hyderabad. We learning VLSI design flow. So in the previous sections, we have seen what is the MOSFET structures, and also now generally we'll see how VLSI design, what is the VLSI design flow. So what is the VLSI design flow? So we'll see what are the different steps involved in designing an IC. So we'll see it one by one. So before we go, all of us know that what is VLSI. VLSI stands for very large scale integration, and in the today's like almost all electronic devices equipments, we are using VLSI ICs. Okay, so the outcome of this very large scale integration is our integrated circuit. So wherein in VLSI, in very large scale integration, what we are doing, the millions of transistors are integrated on the single IC. So this IC is used for different applications, and today we'll see what is the design flow for this. What is the VLSI design flow? So in the VLSI design flow, the first step involved is these system specifications. System specification. So the first step in the VLSI design flow is the system specification. So to design any system, so to design any IC, so whatever purpose we have been designing, so first we will see the design specification. So here we will list out all the specifications of the system that what we are going to design. So for example, let us say we'll record here what should be the performance of the system, then what should be the functionality, and here in the system specification we'll consider all the details about the physical requirements, especially about the area. So when we talk about VLSI, four things are general, that is area, speed and power. So these three constants we have to take care when we're designing when we're designing a VLSI IC. Okay, so and here in the apart from the performance, functionality and area in the system specification, we will list out like what fabrication technology to be used and other technologies, that is the design techniques. Okay, so what design techniques we are using. So all these things will be recording in the will be recording in the system specification. Okay, so that was like, it is called as the high level report of the system. Okay, so like this is the high level specifications, like what are the main specifications of that system what we are going to design. So all these things will be recording in the system specification. So after taking the different specifications like area, speed, power, techniques to be used, so the next step used here is the architectural design. So once we do this, so the next step is the architectural design. The second step in the VLSI design flow is the architectural design. Okay, so I'll take it as an arrow map. So in the architectural design is the second step. So here we will be designing the architecture. So in this step, what we are doing after taking all the system specifications and what the system should perform is functionality, structures, which design techniques to be used. So then we here in the second step will be designing the architecture. Whether he here will take some decisions like whether we have to choose a RISC architecture or a CISC versus a RISC. So which architecture to be used? That is, RISC stands for Reduced Instruction Set Computing, and CISC stands for Complex Instruction Set Computing. So in the architectural design things, we'll take some of the architectural decisions here, that which architecture to be used, whether we have to use a RISC architecture or CISC architecture. Here we we'll be talking about what will be the pipeline structure and what should be the size of the cache memory. Okay, so like whether we are doing using a multiprocessor, so all these things, whether we are using single ALU or multiple ALUs. Okay, so all these things, Okay, so all these things are discussed, are will be done in this architectural design steps, wherein exactly will be designing the architecture. So which architecture will be using, either risk or risk. Then pipeline structure. In the pipelining, what will have, basically we'll be having n number of instructions will be in the pipeline. So after executing each instruction, the next instructions will be ready in the pipeline. So all these things like ALU design, cache memory, what would be the size of the cache memory. So all these things will be done in this second step, that is the architectural design. So once the architectural design is done, the next step in the VLSI design phase is the functional design. Okay, so once we are done with that, once we are done with this, once we are done with this architectural design, we'll check what is functional design means. Here we'll check the functionality of the design, whether the architecture what we have designed is like the functional design will be taken care in this step. So once it is the functional, whether the functionality, so here each time we'll be testing a particular logic here. Okay, and if it is if it is not working functionally, so until and unless the system functionality is proper, so we will be doing this functional design. Okay, so in the functional design we will make sure that the design is working, so design is performing all its functionalities. Okay, so each and every time we'll be checking and we'll be doing this in the functional design. So that is the purpose of this functional design. So once the design is ready, once it is working properly, then we'll go for the layout design. So now we'll be going for the physical design once, that is layout design. Okay, so these three steps will come in the high level design. Okay, so in the high level design, so after that, like in the layout design, so now we'll be discussing about how this design is designed, is put it in the form of the layouts. Okay, so the layout design is done. So after the layout design, then the circuit diagram is done. Okay, circuit design. Okay, let us say like we are having okay, some circuit, let us say. Okay, okay, like this. Okay, so let us say we are having some design. Okay, then the circuit this thing is done. Here you can write ABC. So like these kind of things will be doing it. That is circuit design is done. So the next step is the circuit design. So once this design is done, so then we'll be doing the physical design. So we'll discuss all these things in one by one. Physical. So once the circuit design is done, so we'll be going for the physical design. So in the physical design, the main aspect it should be we have to reduce the area. Okay, so here we will be discussing about some of the concepts like placement, routing. Okay, so all these things are there. So we have to take care of the routing, means all the components in the circuits are to be connected. So that concept is called as routing. Then the placement of the components. Okay, so that is taken care in the physical design. So in the physical design, we'll be using this concept like placement, routing, and other things. So that we'll be using the less area. On a less area, the large number of transistors are manufactured, and we'll make sure that the size of this IC is very small. Okay, so once all this complete design is done, okay, so once the physical design everything is done, then this file will be given for the fabrication. Okay, to the factory. Okay, so that process we call it as fabrication. Okay, so we'll be sending all this file to the factory for the fabrication. That is called as the fabrication process. Okay, so once the fabrication is done, once the IC is ready, so the final step what we'll be doing is the packaging and the testing is done. Packaging and testing. Okay, so these are the steps that we have been. So these are the steps for steps of VLSI design. That is, in the beginning we'll be taking. Let us say we are designing an IC for washing machine. So for what and all the functionalities required for washing machine will be taken care. That is, all the specifications will be included. So that's why it is called as a high level specifications will be taken care. Then after that, the architectural design is done. Herein we'll be discussing about what architecture to be which architecture to be used. Here we'll take some decisions like whether we have to use a risk architecture or architecture depending on the application. So which pipelining, like how many, what should be the size of the pipeline, then how many ALE should be used. Okay, then what should be the size of the cache. All these things will be taken care. So after that, the functional design is done. Okay, then the layout design, then the circuit design. We'll see all these things in detail. Then the physical design. Once it is sent to the fabrication, at the end we'll be taking care of the packaging and the testing. So this is about the VLSI design process. So whatever we have discussed, the same thing is mentioned here. So in the functional design, okay, so the function will be checked for each and every time. Then in the logic design, whatever our function, what we have to perform, that will be put in the form of the Boolean expressions. Okay, so we'll be writing and we'll be designing the circuit design. Okay, so once this circuit design is done, we will going for the physical design. That is, on the IC, how we are going to put this on the IC, how we are going to put the circuit. Okay, so that thing is called as the physical design. Okay, then the fabrication will be giving it to the factory for fabrication. So once it is done, the packaging and testing is done. Okay, so the system specification, as already I have mentioned, so here we'll be taking the specifications will be recorded here. Okay, and in the second thing, the second step in the VLSI design flow is the architectural design. So in the architectural design, basically, as I have mentioned earlier, we'll be taking the decisions like whether we have to use a disk architecture or system architecture, what should be the size of the pipeline, size of the cache, how many ALU should be used, all these things will be taken care. So one example of this architectural, say you can say that the computer. Okay, so the computer, when we are designing a computer, we should see the performance, that is the speed should be taken as one of the architectural parameter. Okay, so like this, the decisions will be taken. Okay, so the next step in this one is the functional design. Okay, so so in this step, what we do is that the main functional units of the systems are identified here. Okay, then the interconnect requirement between the units will be taken. So here in the functional design, we will be taking care about the very three important parameters like area, power, and the performance parameters will be taken care. And here also in the functional design, we will be taking care of the behavioral aspects of the systems. Okay, then like let us say for example, like the multiplication is required. So here exactly in which mode the multiplication to be executed. Okay, so all these things will be taken care. So this is about the behavioral design. So this information leads to improvement the overall design process once we do it. Okay, and the reduction of the complexity in the subsequent phases. Okay, so here in the functional, it is also called as the behavioral design. It provides a quick emulation of the systems and allows a fast debugging of the complete system. So once we design this functional design, so the complete the quick emulation of the complete design can be done. So the behavioral design is largely a manual step with the little or no automation help available. So the functional design, which is also called as behavioral, so this is basically an automated step which it to be done manually. So once we do that, the next step what we discuss is the logic design. So in the logic design, we'll be writing basically whatever the thing we are designing. So we'll be writing the RTL code for it. That is, RTL stands for register transfer logic. Okay. So the control flow, word feed, the register, then arithmetic operations, logical operations of the design that represent the functional designs are derived and tested here. So this complete discussion, what the design should do, will be written in the RTL code. That is register transfer logic code, and RTL is expressed in the HDL. That is, we have two codes, that is VHDL and Verilog. So either we can use VHDL and Verilog coding for this. And by writing this, so all the functionalities what we are willing, all these things will be written in the terms of the registers. Okay. Then in the logical, with the help of arithmetical logical operations, we will be writing this code in the. Okay, so in this step, we'll be writing the ITL is expressed in the hardware description language, and such as VHDL and Verilog language we can use here. So the Boolean expressions are minimized to achieve the small logic design which confirms the functional design. So this logic design of the system is simulated and tested to verify the correctness of the design. So whatever the specifications we have noted down, so for those specifications here we'll be writing the Verilog code or VSDL code, and that will be synthesized. Okay, and here we'll be using some synthesized tools for testing. So these tools produces a RTL description form, a behavioral description of the design. So this is about the completely logical design. So basically in the logical design, we will be writing the code in Verilog or VSDL, and will be testing its functionality, whether it is working properly for all the requirements what we have recorded. So once the logic design is done, that is the code is written, okay, then we'll be doing the circuit design. Okay, so the purpose of circuit design is to develop a circuit representation based on the logic design. So here the Boolean expressions are converted into the circuit. So whatever the code we have written, so that code will be converted into the form of the circuit here. Okay, so the circuit simulation is used to verify the correctness and the timing of the each component. So what all the components timing to be taken care here. So the circuit design is usually expressed in detailed circuit. So in the RTL, we will be recording all those details with the help of the logic synthesis tools. Then once it is done, then the next step is the physical design. So in the physical design, we have taken care of the layouts to be designed here. So in this step, the circuit representation is converted into the geometric representation as stated earlier. So this geometric representation of a circuit is called as a layout. So the complete what we have designed, so that we have to put in the form of the layout on a physical IC. So layout is created by converting the logic components such as like cell macros, gates and transistors into the geometric representation, and which perform the intended logic function of the corresponding component. So here in the physical design, we have to take care of the layout synthesis to be done. So all these things will be taken care in this physical design. Okay, and in the physical design, we'll be going for like placement, routing, all this. The help of these placements and routing, the design is done. So once it is done, then the IC will be given to the fabrication factory for and the industry will get the ICs manufactured. So once the IC is manufactured, so the packaging, testing, and debugging is done. For this, different tools are used here. So chips used to printed circuit boards like PCBs are packaged in dual DIP. So there are different types of packaging also available. So with the help of all these dual in package DIP and QFP techniques, so there are different types of packaging techniques are there. So based on the IC fabrication, so the different types of packaging the packaging techniques are used. So these are some of the the VLSI design flow. Okay. So once yeah, we are done with the VLSI design flow, so we'll see what are the uses of VLSI. Okay, so it occupies a relatively smaller silicon area. So if you see some of the advantages of VLSI is like where we can use it is because of the small area. Okay, uses of VLSI. The areas it occupies is very less, and the manufacturing process is simple, requires few processing. So only few steps are required to fabricating an IC once we have designed. Then high component density, that is the microprocessor and controllers are constructed here. So high density components are being produced here. Then VLSI systems are high performance and cost effective systems. And and VLSI systems are smaller in size. So the earlier days, the sizes of the devices were very huge, big. So because of the VLSI technology, the sizes of the devices is being reduced. Then easier to design and manufacture, that is one of the uses. Then the higher reliability, so the reliability of the VLSI ICs are like this, highly reliable. Then high operating speeds, then design flexibility is there as well too. So once we have done a design, then we can use the same thing again and again, and we can reconfigure also. That is the advantage. Then the high productivity is there, then high functionality. So high productivity in the sense we can at one time we can manufacture thousands of transistors at one time. Then higher functionality is there to provide high functionality compared to the other things. Then the design security is also available. So these are some of the uses of VLSI. Then VLSI chips are widely used in the various branches of engineering, like digital signal processing. Okay, so in almost all signal processing areas, VLSI ICs are being used. Okay, so this is one of the major advantage. So wherein we'll use almost all digital signal processing techniques uses VLSI. Then VLSI, it is also used in multimedia information system, that is internet. Then voice and data communication networks, where also we'll use VLSI. Then we use in wireless LAN, that is local area network. Then reconfigurable computing. Okay, so the reconfigurable computing is the latest technology wherein once the design is done, we can reconfigure it for different for updating its features. So where there also this VLSI industry is being VLSI chips are being widely used. Then VLSI Bluetooth, as you can see, in the Bluetooth VLSI chips are used. Then in the Sonnet. Okay, then the different types of buses like USB buses, PCI, all the interface buses, we use VLSI chips. Then VLSI chips are used in the TVs, DVDs. So here you can see in the washing machine. Okay, so we can see, we can device whatever electronic device we can name. So almost all these devices are being used. Will use the VLSI chips, and in the automobile and the toys industry also. And nowadays, because of the growth in the artificial intelligence and machine learning, the demand for the VLSI IC has been increased, and the VLSI ICs are also used in the electric vehicles. Electric vehicles is a new trending wherein we've been using these VLSI ICs in the electrical vehicles, and VLSI ICs are also used in making the smart cities. Smart cities. So for developing small cities, VLSI chips plays a very very important role. So in the almost all devices, we have been using this VLSI ICs. These are the reference books we have referred for preparing this material. That is the textbook written by A. Pagnal and Kamran. That is a basic VLSI design. Uh, the third edition. This is the ISBN of the book. Then the second book we have referred is Jacob Baker and Harry W. Lee and Boyle. Okay, so the book name is CMOS Circuit Design, and we have used Jan Ravi book. So these are some of the references what we have used. That's it for the today's presentation. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.